We are very happy to have Dr. Nishant Rathee from IISER Mohali. He will be speaking on Rota-Baxter operators and skew brace structures over Heisenberg Group. Over to you, Nishant. Please.
Thank you so much, and I'd like to thank the organizer for this opportunity. So yeah, as Soma told you that I'll talk about this Rota-Baxter operators and some skew-based structures over Heisenberg group. Okay. So like these will be my main content of my talk. Like first I'll talk about some set theoretical solution of Yang-Baxter equation and to give you some background. Then I'll give you some examples of solutions and talk about these algebraic structures, very interesting algebraic structures called skew left braces. Then we'll talk about Rota-Baxter operators and its connection with skew left braces, and then we'll finally compute some examples of these operators over Heisenberg group and Heisenberg Lie algebra both. So okay. So what do you mean by a set theoretical solution of a Yang-Baxter equation? Like suppose you have a map from x squared to x squared, then you can define a map from x cubed to x cubed. Like usually we do in tensor product by doing R tensor ID. So here we just do R cross ID. So like we can define R12 by R is acting on first two component and the last component remains as it is. Similarly, R23 we can define by R is acting on the last component and first component remains as it is. So Yang-Baxter equation is an equation in the composition of mappings where this just a position represent the composition of maps, like because all maps are from x cube to x cube, so composition makes sense. So like if you have a map from x square to x square which satisfies this composition R12, R23, R12 is equal to R23 composed with R12 or composed with R23, then we'll call this map is a solution of Yang-Baxter equation. So if you look closely, this relation is somewhat seems like the relation we use in the presentation of braid groups. So this equation is also known as the braid equation as well. Actually, this is braid equation. The Yang-Baxter equation is somewhat different. But looking at the solution is equivalent, because if you have a solution of a Yang-Baxter equation, you twist it like flip it, then you will get a solution of braid equation. And you have a solution of braid equation, you flip it, you will get a solution of Yang-Baxter equation. So people vaguely say that this is the Yang-Baxter equation in modern terms. So yeah, I hope this equation is clear to everyone. This is quite looking like weird looking equation, but this is what we use. So okay, so suppose we have a solution of a Yang-Baxter equation, then every mapping to coordinate could be written in this form, fxy and gyx. Like this is the very usual thing. Actually, it is difficult to classify all the solutions of Yang-Baxter equation. So people characterize this solution in some certain by putting certain conditions on this map fx and gy. So if these both maps are bijection and this map R itself are bijection, then the solution is called non-degenerate, and we'll talk about that solution only. So okay, so as we defined that R, fx, and gx are bijections for all x, then the solution is called non-degenerate, and this is the these are the wide. This is also a big class of solution which people study. So okay, so if its square goes to identity, then the solution is called involutive as usual. So let's see some examples. So consider flip map from any set. Then it will be a solution of Yang-Baxter equation. And of course, this is not non-degenerate, but it is solution. Suppose you have a set and you have two bijections from x to x, such that sigma tau is equal to tau sigma. Then this map Rxy going to sigma x comma tau y is also a solution of Yang-Baxter equation. So let's see some more examples. So suppose you have a cyclic group of order n, then you can define Rxy to be of this form, like Rxy going to 2x minus y comma x, and Rxy is equal to y minus x comma x plus 1. So this will again form a solution. If you have any group G, then you can define the map R by conjugating the y by x and x. So actually this is the solution arising from algebraic structure called quandles. And the another thing you can define by using Rxy is equal to xy inverse x inverse from x square. So you can see that there is a connection between the groups and the solution. It is easier to produce this solution if you have a group structure on the set. That we're going to discuss in this talk. So, okay, let me tell you some background. So, Yang-Baxter equation is named after the physicist C.N. Yang and R.J. Baxter. The equation is initially surveys in the following independent studies. The first many body problems in quantum mechanics, it is done by Yang. If you want to really check out the background, then you can see this paper. And the another is by Baxter, the 8 vertex model of statistical mechanics, where reference is given this. So I really don't know much about the physics because these equations are really coming from physics. But if some of you is really interested in background and knowing that how these equations come up, you can look at these references. So okay, but these equations are mathematically also very interesting. That's why I'm doing this. So okay, so let's define an algebraic structure called skew left base. So suppose you have a set and there are two group operation on it. The one is represented by a plus and another one is represented by a circle. And the following compatibility conditions hold between the two group operations. So that a circle b plus c is equal to a circle b minus a plus a circle c for all ABC. Like minus a represents the inverse of a in the a plus. And please note here that this a plus is need not be an abelian group. I know it is confusing writing the group operation by plus. People usually assume that it is an abelian operation, but actually Rump defined these objects initially over abelian groups only. Later in 2017, Vendramin and Gurneri generalized these objects to non-abelian thing. But it is super convenient in the calculations of using this plus operation. So that's why I'm still using here plus, but this need not be abelian. So okay. So what are the example of this? So if you take any group with both of the group operations are same, then this will be a skew brace. That they are called trivial skew brace. And this is also a very classical example. So if you have a radical ring means like Jacobson radical is equal to the full ring, or Jacobson radical of a ring forms a radical ring. So and you define this operation a circle b is equal to a plus b plus a dot b. Then it also form a brace. If the additive group is abelian, then these structures are called braces. If this is non-abelian, then we call it skew braces. So radical rings are the examples of skew left braces. If you have a cyclic group over n, and suppose D is a divisor of n such that every prime divisor of n divides D, then this A circle B is equal to A plus B plus DAB. This also form a skew brace structure over Zn. Okay. So like first I define an equation, then I define some algebraic structure. Then you ask like what is the connection between them? So this is the connection. This is proved by Vendramin and Gurneri in 2016. So suppose you have a skew left base, then you can define an action of additive group on the action of multiplicative group on the additive group by the map lambda, where lambda a b is equal to given by minus a plus a circle b. So you can see if the group is trivial, then these two will cancel out and you will just have b. So this will be an homomorphism, and if you define the map R from a cross a to a cross a, given by this lambda a b and by this complicated formula. I don't want to pronounce all of this, but yeah, this will defines a non-degenerate solution of Yang-Baxter equation. And furthermore, this solution is involutive if and only if this additive group is abelian. Yeah. Yeah, okay. So here we define an algebraic structure. Okay, yeah, I want to say that the converse is also true. Suppose you have a solution of a Yang-Baxter equation, then you can define a skew left base structure using that, but the connection is not one-to-one because the skew base structure you define from the solution is always infinite. So like it's not possible to define a finite skew brace from the solution. The techniques still we have now. So yeah. So like I want to remark out that I talked about the skew-based structure, but there are many other algebraic structure people used to study in this setting. For example, semi-braces, inverse semi-braces, weak braces, Rex, quantals, etc. Also, my postdoc supervisor, mainly works on these Rex and quantals. So yeah. Okay, so let me give you. I have given you the examples over of skew-based structures over finite group. Now let me give you an example over infinite group. So define this operation over Z. M circle n is equal to minus 1 m n plus n. So by this formula. So this will be a left brace structure over Z. And this weird looking group is actually infinite diagonal group. So yeah. So there are very few examples known over infinite groups because using computer calculations and the connection between holomorph, people have calculated some examples over finite groups, like let's say the classification over p square, p cube, even p power 4 is given, but like there is no skew-based structure is known over R, C, like real number, GL and C. So that will be the purpose of this talk. Like we'll try to give you skew left brace structure over Heisenberg group of dimension 3. So okay. So okay. Let us define the Rota-Baxter operators, which are some tools of studying skew bases. Suppose you have a group G and you have a set map from G to G, and it satisfies again this weird looking condition RGX into RGY, and RGX and Y is conjugated by RGX. Then this operator is called Rota-Baxter operator. Okay. Yeah, you can see that if G is abelian group, then it is just a homomorphism. So you can view it as a twisted homomorphism of groups. So its example, like suppose you have a trivial map, everything going to identity is an example of Rota-Baxter operator. X going to X inverse is an example of a Rota-Baxter operator on G. And this is a very important example. We'll not use this in our talk, but in general, the third example is proved to be very useful in this area. So if you have exact factorization of a group, suppose G is equal to H into L, then you can define a map from G to G by HL going to L inverse, where of course H belongs to H and L belongs to L. And this is also a Rota-Baxter operator on G. This is useful because like whenever you have a semi-direct product, you have exact factorization. And people prove many structured results using this Rota-Baxter operator. So okay. So first I defined the Yang-Baxter equation, then I defined skew left basis, then I defined Rota-Baxter operators. So like why I have defined this? So like there is a relationship between Rota-Baxter operators and the skew left basis, which is given by Gubrev and Bardakov in 21. So suppose you have a Rota-Baxter group or a Rota-Baxter operator GB. So then the operation G circle H going to G dot BGH BG inverse. Then define this operation defines a group structure on G, and together with the original group operation on G, this turns out to be a skew left base. So okay, so you have a Yang-Baxter equation, then we have defined skew left basis which induces solution of Yang-Baxter equation. Then we define Rota-Baxter operator which induces skew left basis. So this is the connection between Rota-Baxter operators and skew left base structures. Okay. Yeah, so I want to remark that this definition of Rota-Baxter operator or group has been generalized to the semi-groups as well, like something called Clifford semi-groups. And there is a generalization of braces called dual weak braces that's also been studied. So yeah, this is a recent generalization of these operators. So now we have seen that every Rota-Baxter operator induces a skew left base structure. So the now question arises: can every skew left base structure on a group G can be induced by a Rota-Baxter operator? This is an actual question. But you can see, like suppose G is an abelian group, then this group this circle operation is always same as the additive group operation, because this dot is abelian. So you cannot produce non-trivial skew-based structure over an abelian group using Rota-Baxter operators. This is trivial. This problem is trivial to answer. The real problem is like as you can see that when you define this circle operation, the associated lambda map of this cube base takes values inside the inner automorphism group of G. So the real non-trivial question is that suppose you have a group G, so that its associated lambda map taking values inside the inner automorphism of G, then can that skew left base structure can be induced by Rota-Baxter operator? This is a non-trivial question, and this is proved by Kranti and Stefanello in 23. So they are skew left base structure for which associated lambda map take values inside the inner automorphism group, but they yet cannot be induced by any Rota-Baxter operator. And the examples are Heisenberg group, are also Heisenberg group. Yeah, they have used group cohomology and the connection between second cohomology and extensions of group, and they constructed such examples. So okay. So but something weaker is true. Every skew left base structure on a centralized group with associated lambda map takes value inside the inner automorphism group can be induced by Rota-Baxter operator. So actually these Rota-Baxter operators are more useful when the center of the group is relatively small. Then you can induce most of the skew base structure using these operators. Okay. So now we have defined the Rota-Baxter operator over group. Let's define the Rota-Baxter operators over Lie algebra. So actually there are three versions of this Yang-Baxter equation. We have mentioned the set theoretical Yang-Baxter equation, but there is classical Yang-Baxter equation, associative Yang-Baxter equation. So the associative Yang-Baxter equation is over associative algebra. You replace the set by an associative algebra and replace the product by the tensor product. And in classical Yang-Baxter equation, you replace the algebra by the Lie algebra, and the product is by tensor product. So Rota-Baxter operators or Lie algebra are studied since 1980s or 1970s because they induces solution of classical Yang-Baxter equation. So yeah, so let's see what is the definition of a Rota-Baxter operator over Lie algebra. Suppose you have a Lie algebra and you have a linear map from G to G, which satisfy this this weird identity. Rxy is equal to R of Rxy plus X Ry plus Xy. So again, here you can see if G is an abelian Lie algebra, like Lie bracket is 0, then every linear map is a Rota-Baxter operator. So they are also useless over abelian in abelian case, as similar to group. So similarly, we call this pair G comma R a Rota-Baxter Lie algebra. Okay. So let's see the examples of some Rota-Baxter operators over Lie algebra. Of course, the zero map, everything going to zero, is an example of a Rota-Baxter operator over any Lie algebra. X going to minus X is a Rota-Baxter operator over G. And similar to the groups, suppose you have a decomposition of G in its Lie subalgebra G plus and G minus, then you can define a map X plus X minus going to minus X. Then this will be again a Rota-Baxter operator on G. So actually, Rota-Baxter operator over groups are defined very recently in 2020, but these operators are known since 1980s. So actually, what they did, they define an operator on a group so that it differentiation its tangent map at identity form satisfy this identity. So that is the motivation defining behind the Rota-Baxter operator over groups. But we utilize them in some another sense. So like as this is theorem. So suppose we have a Rota-Baxter operator over Lie group. Of course, this R map I'm assuming to be smooth, because over Lie group you assume everything to be smooth to differentiate that. And suppose G be the tangent space of G, then you can define the tangent map of R at identity. Then this map R defines a Rota-Baxter operator over the Lie algebra G. So this is very recent result. So now we want to explore the converse of this theorem. Yeah. So actually, what they have given is, suppose you have a Rota-Baxter operator over Lie group, then you can induce a Rota-Baxter operator over Lie algebra. But like finding Rota-Baxter operator over group is the real tricky case. Like similar to the like people use this theme in Lie theory very well. So suppose you have something over Lie group, you differentiate and induce over its Lie algebra, like homomorphism or representations. But the converse we can do only in some rare cases, like more precisely in, I think, simply connected case. So in simply connected case, you can go back. Like suppose we have something over Lie algebra, you can induce it over the Lie group, and that's what we're gonna do here. So because like the motivation is clear, because we want to find out the Rota-Baxter operators over Lie algebra, then we want to induce them over the Lie group, then we want to see what will be the skew-based structures, because we already seen that Rota-Baxter operators define skew-based structures over a group. So let's do this. So okay. So like for that we need this theorem. So suppose we have a group G. Then Rota-Baxter operators on G are in one-to-one correspondence with the subgroups of this semi-direct product G, such that the projection of the second coordinate of H onto G is a bijection. So like the Rota-Baxter operators on G are in one-to-one correspondence with some special type of subgroups of this semi-direct product group. So the proof is really simple. Suppose you have a Rota-Baxter operator over G, then you can define its graph. Graph is like just Rx, X. Then this will form a subgroup of this semi-direct product. And conversely, if you have a subgroup of this semi-direct product such that the projection of the second coordinate onto G is a bijection, then you can associate the first coordinate to the second one, and it will define a Rota-Baxter operator. So this is a very nice connection between the operators and the subgroups of a group. And the similar connection holds for Lie algebra as well. Suppose you have a Lie algebra, then the Rota-Baxter operators on G are in one-to-one correspondence with the Lie subalgebras of B, such that the projection of the second coordinate from B onto G is a bijection. Again, here the semi-direct product over Lie algebra makes sense, and this small ad is small. This capital ad is, I forgot to tell. This capital ad is the conjugation action, like Gx on G by conjugation. So ad x of y is equal to xy x inverse. And so this small ad is the tangent map of capital ad, and this is defined as ad xy going to Lie bracket xy. So these are very standard terms in this theory. So okay, so the proof follows similar. Suppose you have a Rota-Baxter operator, then you define a graph of it, Rx, X. Then this will form a subalgebra of this. And suppose you have a such subgroup, then you associate first coordinate to the second coordinate. It will define a Rota-Baxter operator over that Lie algebra. So the proof is really very similar to the group case. Okay. So we have the following theorem proposition as well. This semi-direct product G is isomorphic to just the direct product, and this semi-direct product of Lie algebras is isomorphic to the direct product of Lie algebras. Actually, I need to prove this theorem because I want to calculate the exponential map from this semi-direct product Lie algebra to the semi-direct product group. In general, there is no way you can calculate the exponential map of a semi-direct product. Actually, I want this exponential map in terms of the exponential map of G, but that is also, there is no direct way to do that. So what I did, I identify this semi-direct product with a known group, and then we know the exponential map of this direct product. This is just xy going to e power x comma e power y. So a direct product case is really simple. So yeah, that's why I approved this theorem. So the proof is really simple. So you can define the map psi from this semi-direct product to direct product as G going to G comma H, and this will form a isomorphism, and you differentiate it. Then it will define a isomorphism of Lie algebra. So here it is very similar to the group case, xy going to y plus x comma x. So these are the isomorphism between semi-direct product to direct product in both group and Lie algebra case. So yeah, so it is well known that if you have a Lie algebra G of a Lie group G, so small g and capital G, so it is known that the Lie algebra of the Lie group, this semi-direct product, Lie algebra of the semi-direct product is the semi-direct product of the Lie algebras. And the direct product of a Lie group, and when you have direct product of Lie group, its Lie algebra is just the direct product of the Lie algebras. So it is easy to see that this phi map is the tangent map of this capital phi at identity. So okay. So using this isomorphism, we know the exponential map of this. So using that, we have calculated the exponential map of this from this semi-direct product Lie algebra to semi-direct product group. So the map is given by exponential of xy going to exponential of x comma exponential of x plus y into e minus x. So you need to prove that this is the exponential map. There are some certain properties it satisfies, and the differentiation of one parametric subgroup at identity is x, something like that. You have to prove this. So yeah, but I'm omitting this proof. This is just direct calculation. So okay. Now we have computed the exponential map. Now come to our case. So recall that Heisenberg group H is of 3 cross 3 matrices over C is a matrix Lie group containing these upper triangular matrices where 1 1 1 at diagonal, and it's Heisenberg Lie algebra, its corresponding Lie algebra. It is a Lie group, of course, and its Lie algebra is given by these strictly upper triangular matrices with the ACB. So yeah, so these are very well known facts. So yeah, this it is easy to see that the set the set x y z, where x y z are defined this way, these matrices, this form a basis of Heisenberg Lie algebra, and they satisfy this relation. The xy is equal to z, and z is central element in Lie algebra, which means that Lie bracket is 0. So yeah, so these are also very well known things. Yeah, okay, exponential map. In general, exponential map is quite tricky to define, but in the case of matrix Lie group, it is just the power series expansion of E. Like you write the power series expansion of Ex, which is 1 plus x squared 2 factorial plus x cubed plus 3 factorial, and you put a instead of x. So that's the exponential map in the case of matrix Lie groups, which is relatively very simple. So, but in case of Heisenberg group, it is even more simpler. It will terminate after 3 steps. It is 2-step nilpotent group, and if you have a matrix X of this form, ACB, then its exponential, its imagined exponential map is this matrix, given by this matrix. So yeah. So yeah, in case of nilpotent Lie groups, the exponential map is a diffeomorphism. Like diffeomorphism means it is a bijection and it is smooth. So actually, we don't need smoothness in this in our talk, but the bijection part is very important. But this is the general fact about nilpotent Lie groups. But this identity holds true only for Heisenberg case. This EH is diffeomorphism is true for in general nilpotent Lie groups, but this identity is valid only for Heisenberg Lie group of dimension 3. So okay, so now we have computed the exponential map from semi-direct product Lie algebra to semi-direct product of group. So in case of Heisenberg group, this turns out to be this map. The exponential map is given by this exponential of xy going to e power x comma e power y Lie bracket xy upon 2. So this is the exponential map in case of Heisenberg, semi-direct product of Heisenberg Lie group. So now our aim is to calculate all the Rota-Baxter operators over Heisenberg Lie algebra. Then we, using the exponential map, will transfer them to the Lie group, and then we'll list the Skew-based structures, hopefully. So okay. So like okay, so now Heisenberg Lie algebra is what I mentioned 3. So every linear operator on B can be represented by a 3 cross 3 matrix with entries in C. So by the skew symmetry, okay, by the skew symmetry of the Lie bracket, and using that Z is central, in order to show that a map R is a Rota-Baxter operator, we only need to check that it satisfies this identity. So in the case of Heisenberg Lie algebra, our case is really simplified. So we just only need to check the which matrices satisfy this identity. So like okay, I have solved what I did. Um, I put the values of x and y, and instead of r, I put this matrix, and I solve this equation. So and the solution I got my Rota-Baxter operators. So I can further improve this result by using the automorphism of Heisenberg Lie algebra. And using the automorphism of Heisenberg Lie algebra, I can transform this matrix block. For that, you have to see the automorphism of Heisenberg Lie algebra. I'm not mentioning that here. So you can really transform this 2x2 matrix block into its Jordan canonical form. You cannot transform whole matrix into Jordan canonical form, because the automorphisms are very restricted. Yeah, in case of, because you can only conjugate by an automorphism of Lie algebra, not just any arbitrary invertible matrix. So like suppose we have arbitrary Rota-Baxter operator on B, then up to Jordan canonical form of this matrix block, we have the following Rota-Baxter operators over B. Of course, like this looks a little bit weird, but like this is what I got after solving these equations. I use Mathematica to solve them, but like the equations are not very difficult. One can solve them by hand also, but like I use Mathematica. So and they look like this. So every Rota-Baxter operator over the Heisenberg Lie algebra of dimension 3 up to Jordan canonical form of this matrix block is of this form. Okay. So now we have completed our one task, that we have computed all the Rota-Baxter operators over Heisenberg Lie algebra. So this is just a direct computation. So now the fun part. So suppose you have a Rota-Baxter operator on Heisenberg Lie algebra, and graph R. Of course, graph R is a sub-Lie algebra of the semi-direct product, we know. And then we can send this Lie sub-algebra to the semi-direct product Lie group using the exponential map, and that's why we have calculated the exponential map. So it turns out that if you have a graph of a Rota-Baxter operator over Lie algebra, and you transfer this under the exponential map, then this forms a subgroup of this semi-direct product Lie algebra, such that the projection of the second coordinate of onto H is a bijection. So that's what we have required. We have already showed that these kind of subgroups are already in one-to-one correspondence with the Rota-Baxter operators. And actually, in this case, this happened because exponential map is already a bijection. So yeah.
Yeah,
more
Nishant, can we wrap up within 1 or 2 minutes?
Yeah, I'll try.
Yeah.
So like yeah. So every Rota-Baxter operator on B, more precisely, it is given by this formula, like x plus rx upon 2 is equal to rx. So yeah. Now, okay. So this is again we simplified, because the form of this matrix is somewhat complicated. So we using the substitution, we further simplified this, and it turns out that this matrix, every matrix will go to this kind of matrix under this Rota-Baxter operator, where this P is given by this complicated formula. So okay, so finally the skew left brace structure over R is given by we know the formula. This is given by this multiplication, and like my question is that suppose can we find more such actions of G or G such that this semi-direct product is isomorphic to some non-Lie group. So this is a question. If we can find more such actions, then we can find more skew-based structures over any Lie group G. So these are some references. Thank you.
Thank you, Nishant, for the wonderful talk. Any questions? I have a nice question to ask. So given any group, if you consider all the set of all Rota-Baxter operators on it, when is this set infinite? Like
over a finite group, it can never be infinite, because they are all just set maps. It can maximum G power G.
Right.
So Also, like when you see this,
One-to-one
for
correspondence that you have given, is that?
yeah, between the subgroups.
Hmm.
So just let me see.
From there, can you say something or?
No, no, like over infinite group you are talking
Yeah.
because of uh, okay, okay, just so it depends on what kind of subgroups this semi-direct product admits. Like if it admits infinite of these kind of subgroups, uh, just uh, so if it admits infinite number of subgroups which have this property, the projection onto second coordinate is a bijection, then the Rota-Box operators should be infinite. But for infinite groups, I
How do
I
you
don't know.
classify? Is there a classification for these kinds of these groups which admit this structure?
So they are the graph of some Rota-Box operator.
There is a
They are graphs of some Rota-Box operator. They are graph, like suppose you have Rota-Box operator on G, then you can define the graph by Rx, X. Then these subgroups are exactly the graph of Rota-Box operators. In general, there is no way to characterize this or infinite groups, but for Heisenberg group in this talk we have done.
I see. I see. All right. Thank you. Any other questions? If not, let us thank the speaker.